For decades, the digital world has been defined by the classical computer, a marvel of engineering that has reshaped our lives. But as we push the boundaries of what's possible, we're encountering problems that even the most powerful supercomputers struggle to solve. Imagine a machine that doesn't just process information faster, but processes it in a fundamentally different way, leveraging the very fabric of reality at its most minuscule scale. This is the promise of quantum computing, a frontier where the rules of the everyday world give way to something far stranger and infinitely more powerful. At the heart of every classical computer lies the bit, a binary unit of information that is either a 0 or a 1. This simple, elegant system has allowed us to build vast digital empires. However, the classical bit holds a fundamental limitation: it can only exist in one state at any given moment. To solve incredibly complex problems, classical machines must process each possible pathway sequentially or in parallel with many bits, a method that quickly becomes unwieldy when the number of variables explodes. The need for a new paradigm becomes evident. Quantum computers shatter this classical barrier by harnessing the peculiar laws of quantum mechanics. Unlike their classical counterparts, these machines don't rely on bits, but on qubits, quantum bits. A qubit, fundamentally, is still a two-state system, much like a classical bit. However, the way it exists within those states is profoundly different. This difference is what gives quantum computers their extraordinary power and allows them to tackle problems that remain intractable for even the most advanced supercomputers we have today. It's not just a speed upgrade, it's a paradigm shift. To understand the quantum advantage, we must first grasp the core distinction between a classical bit and a quantum qubit. While a bit is definitively 0 or 1, a qubit exists in a much more fluid state. This fundamental difference unlocks capabilities that appear almost magical from a classical perspective. It's the difference between flipping a light switch on or off, and having that switch exist in a state of both on and off simultaneously, ready to influence other switches in complex, interwoven patterns. This duality is foundational to quantum computing's power. The first pillar of quantum computing's power is superposition. Imagine a classical bit as a coin lying either heads up or tails up. A qubit, however, can be both heads up and tails up at the same time. It can exist in a combination of all its possible states simultaneously. This isn't just a metaphor, it's a physical reality governed by quantum mechanics. For a single qubit, this means it can be 0, 1, or any blend of the two, existing in a probability cloud until measured. This property allows a single qubit to store far more information than a classical bit. The true impact of superposition becomes clear when we consider multiple qubits. With just two classical bits, you can represent four possibilities: 0, 0, 0, 1, 10, or 11, but only one at a time. Two qubits in superposition, however, can simultaneously exist in all four of those states at once. With 3 qubits, you get 8 possibilities. For n qubits, you have 2 to the power of n possible states simultaneously. This exponential growth in representable information is staggering. It allows quantum computers to explore multiple computational paths concurrently, a feat impossible for classical machines. This ability of qubits to exist in superposition of states is often referred to as quantum parallelism. Instead of computing one outcome at a time, a quantum computer, in theory, can perform a calculation on all possible inputs simultaneously. Imagine searching through a maze. A classical computer would try one path after another. A quantum computer, through superposition, could explore every single path at once, significantly reducing the time needed to find the solution. This is not mere speed, it's a fundamentally different approach to problem solving, tackling many scenarios concurrently. However, there's a catch. When you measure a qubit in superposition, it collapses into a definite classical state, either 0 or 1. You only get one outcome. This is akin to observing our spinning coin. Once it lands, you see either heads or tails, not both. The trick in quantum computing is to design algorithms that manipulate the probabilities of these outcomes, ensuring that the desired answer has a much higher chance of being measured. This careful choreography of probabilities is where the true art of quantum programming lies, guiding the system towards the correct solution before observation. The second, and perhaps even stranger, pillar of quantum power is entanglement. Entangled qubits are intrinsically linked, regardless of the physical distance separating them. If you measure one entangled qubit and find it to be a zero, you instantly know the state of its entangled partner, even if it's light years away. This is not communication, as no information is transferred faster than light. Instead, it's a shared fate, a correlation so profound that Albert Einstein famously dubbed it spooky action at a distance. It's a connection that transcends classical intuition. Imagine two coins, perfectly entangled. You flip one, and it lands heads. Instantly, you know the other coin, no matter where it is, must be tails. This instantaneous correlation is the essence of entanglement. In a quantum computer, this means that the state of one qubit can provide information about the states of others, allowing for incredibly complex and interconnected computations. It's this intricate web of relationships that allows quantum systems to process information in ways that are simply impossible for classical computers, where each bit operates independently. When superposition and entanglement are combined, the power of a quantum computer becomes truly immense. Superposition allows a small number of qubits to represent an exponentially vast number of states, exploring countless possibilities simultaneously. Entanglement then creates correlations between these qubits, allowing the simultaneous exploration of these states to be coherent and meaningful. It's like having an orchestra where each instrument can play every note at once, and all instruments are perfectly synchronized and respond to each other's slightest tremor. This synergy is what unlocks the extraordinary computational advantage. The true magic happens when these quantum properties are harnessed by specific quantum algorithms. These aren't just faster versions of classical algorithms, they are entirely new computational recipes designed to exploit superposition and entanglement. They cleverly manipulate the probabilities of outcomes, amplifying the correct answer while canceling out the wrong ones, effectively sifting through vast numbers of possibilities in parallel. This is the art and science of quantum programming, where engineers craft specific sequences of quantum operations to coax the desired information from the probabilistic quantum realm. One of the most famous examples of a quantum algorithm is Peter Shor's algorithm for factoring large numbers. Classically, factoring very large numbers is incredibly difficult and time-consuming, forming the basis of much of modern cryptography, like RSA encryption. Shor's algorithm, however, could factor these numbers exponentially faster. This poses a significant theoretical threat to current cybersecurity protocols, demonstrating the profound disruptive potential of quantum computing. It's a stark reminder that a new era of computational power could rewrite the rules of digital security. Another groundbreaking algorithm is Loewe-Grover's algorithm, designed for searching unsorted databases. Classically, finding a specific item in an unsorted list of n items takes, on average, n/2 queries. Grover's algorithm can do this in approximately the square root of n queries. While not an exponential speedup like Shor's, it's still a significant quadratic improvement, especially for massive datasets. This has implications for fields ranging from database management to artificial intelligence, offering a pathway to significantly accelerate data retrieval and pattern recognition tasks in the future. Despite their power, quantum computers also operate under unique constraints. One such constraint is the no-cloning theorem, a fundamental principle of quantum mechanics. It states that it is impossible to create an identical copy of an arbitrary unknown quantum state. This means you cannot simply duplicate a qubit's information without disturbing the original. This theorem has deep implications for quantum communication and error correction, preventing easy backups or duplication of sensitive quantum information, making the handling of qubits even more delicate and complex than classical bits. The incredible properties of superposition and entanglement come at a cost. Qubits are extraordinarily fragile. They are exquisitely sensitive to their environment. Even the slightest vibration, stray electromagnetic field, or temperature fluctuation can cause them to lose their quantum state, a phenomenon known as decoherence. Once a qubit decoheres, it loses its superposition and entanglement, essentially collapsing into a classical state, rendering its quantum information useless. Protecting qubits from this collapse is one of the most significant engineering challenges in building a functional quantum computer. To combat decoherence, quantum computers are typically housed in highly specialized environments. This often involves cooling qubits to temperatures colder than deep space, near absolute zero, to minimize thermal noise. They are shielded from electromagnetic interference and physical vibrations in heavily insulated chambers. These extreme conditions are necessary to maintain the delicate quantum states for long enough to perform calculations. The engineering feats required to achieve and maintain these conditions are immense, pushing the boundaries of materials science and cryogenic technology to their absolute limits. Even with optimal environmental control, errors are inevitable. Qubits are inherently noisy. This leads to another critical challenge: quantum error correction. Unlike classical error correction, where you can simply copy a bit to check for discrepancies, because of the no-cloning theorem, quantum error correction is far more complex. It involves encoding a single logical qubit into multiple physical qubits, creating redundancy in a quantum mechanical way. This intricate process is essential for building fault-tolerant quantum computers that can reliably perform complex computations. The need for error correction means that a single stable, reliable logical qubit might require hundreds or even thousands of highly fragile physical qubits to exist. This ratio dramatically increases the scale required for practical quantum computers. Instead of needing, say, 100 qubits for a calculation, you might need 100,000 physical qubits. This gap between the number of available physical qubits and the number of fault-tolerant logical qubits needed for robust computation is a major hurdle that researchers are diligently working to overcome, pushing towards ever larger and more stable quantum systems. There are several competing technologies for building qubits, each with its own advantages and challenges. One of the most mature approaches uses superconducting circuits, tiny loops of metal cooled to near absolute zero. At these temperatures, electrons can move without resistance, and these circuits can behave as artificial atoms, creating quantum states. Companies like IBM and Google have made significant progress with superconducting qubits, showcasing their potential with increasingly larger processors. They are highly scalable in principle, but very susceptible to noise and require extreme refrigeration. Another leading contender is trapped ion technology. Here, individual atoms are ionized, given an electrical charge, and then suspended in a vacuum by electromagnetic fields. Lasers are used to cool these ions and manipulate their quantum states. Companies like IonQ are at the forefront of this approach. Trapped ions generally boast longer coherence times and higher fidelity, fewer errors, compared to superconducting qubits. However, scaling them up to large numbers of interacting qubits presents its own unique set of engineering challenges, especially when precisely controlling individual ions. Beyond superconducting and trapped ions, researchers are exploring a diverse array of other qubit technologies. These include topological qubits, which are theorized to be inherently more robust against decoherence due to their exotic topological properties, though they remain largely theoretical. Photonics-based qubits use light particles, photons, to carry quantum information, offering advantages in communication. Neutral atom qubits, quantum dots, and even diamond impurities are all actively being investigated, each bringing unique strengths and weaknesses to the table in the global race to build a scalable and stable quantum computer. Just as classical computers use logic gates, and, or not, to perform operations on bits, quantum computers use quantum gates to manipulate qubits. These gates perform reversible unitary transformations on qubits, preserving their quantum information. Single qubit gates can rotate the state of a qubit on its block sphere, moving it between superposition states. Two qubit gates, such as the CNOT controlled NOT gate, are particularly crucial as they are responsible for creating entanglement between qubits, an essential step for any complex quantum computation. These gates form the elementary building blocks of quantum algorithms. Programming a quantum computer is vastly different from writing code for a classical machine. Instead of sequential instructions, quantum programs often resemble circuits, specifying a series of quantum gates to be applied to qubits. Developers use specialized quantum programming languages and SDKs, software development kits, to design these circuits, orchestrating the superposition and entanglement to guide the computation towards a desired outcome. Understanding the nuanced interplay of these quantum phenomena is paramount, requiring a deep grasp of quantum mechanics, unlike classical programming which abstracts away the physics.
We are currently in the NISQ era, noisy intermediate-scale quantum.
This means today's quantum computers have a modest number of qubits, tens to a few hundreds, and are still quite noisy, meaning qubits decohere quickly and errors are frequent.
They are not yet fault-tolerant.
Despite these limitations, NISQ devices are powerful enough to explore fundamental quantum phenomena and even demonstrate quantum advantage for specific, highly specialized problems. This era is crucial for learning, experimenting, and refining both the hardware and the algorithms for future, more robust machines. The term quantum advantage, sometimes called quantum supremacy, refers to the point where a quantum computer performs a computational task that is practically impossible for the fastest classical supercomputer to accomplish in a reasonable amount of time. It doesn't necessarily mean solving a useful problem, but rather demonstrating the fundamental superiority of quantum computation for certain tasks. It's a critical milestone, proving the theoretical power of quantum mechanics can be translated into tangible computational superiority, even if only for highly specialized, benchmark problems.
In 2019, Google's Sycamore processor achieved a landmark moment by demonstrating quantum advantage.
Their 53-qubit machine performed a specific random circuit sampling task in 200 seconds, a calculation that they estimated would take the world's fastest classical supercomputer, Summit, approximately 10,000 years to complete. While the task itself had no immediate practical application, it was a profound demonstration of the raw, unadulterated computational power inherent in a quantum system, unequivocally proving that quantum computers can indeed outperform classical ones on certain problems. To understand why quantum computers are so powerful for certain problems, consider the challenge of simulating complex molecular interactions.
A classical computer would need to track every atom and electron individually, a task that quickly becomes impossible for even moderately sized molecules. The number of variables grows exponentially, quickly overwhelming even supercomputers. Simulating a molecule with just a few dozen atoms can exceed the storage capacity of all the classical computers on Earth combined. This is where quantum mechanics itself offers the solution, by using quantum systems to simulate other quantum systems. Quantum computers hold immense promise for drug discovery and materials science.
By accurately simulating molecular behavior at the quantum level, scientists could design new drugs with unparalleled precision, understand protein folding more deeply, and create novel materials with desired properties from scratch. This could accelerate the development of life-saving medicines, revolutionary catalysts, and even superconductors, dramatically reducing the time and cost associated with traditional research and development. It's a fundamental shift in how we approach the design and understanding of matter itself. The impact of quantum computers on cybersecurity is one of the most widely discussed applications. As mentioned with Shor's algorithm, quantum machines could theoretically break widely used public key encryption schemes, such as RSA, which secure everything from online banking to classified communications. This necessitates the development of post-quantum cryptography, new encryption methods designed to be resistant even to quantum attacks. The race is on to develop and implement these new standards before powerful, fault-tolerant quantum computers become widely available, potentially preventing a global cybersecurity crisis. Artificial intelligence and machine learning stand to gain tremendously from quantum computing. Quantum algorithms could enhance machine learning models by accelerating training, enabling more complex pattern recognition, and improving optimization tasks. Imagine AI that can process vast datasets with unprecedented speed, identifying subtle correlations currently invisible to classical algorithms. This could lead to breakthroughs in medical diagnostics, financial forecasting, and the development of truly intelligent autonomous systems, fundamentally reshaping the landscape of artificial intelligence as we know it.
Many real-world challenges, from logistics and supply chain management to financial modeling and traffic flow, are essentially complex optimization problems. Finding the absolute best solution among an astronomical number of possibilities is often intractable for classical computers.
Quantum annealing, a specific type of quantum computation, is particularly suited for these types of problems. It can find optimal or near-optimal solutions much faster, potentially revolutionizing industries that rely on efficient resource allocation and complex decision-making processes, leading to unprecedented efficiencies and savings. In the financial sector, quantum computers could enable more accurate and faster risk analysis, portfolio optimization, and fraud detection. The ability to simulate complex market dynamics and model probabilistic outcomes with greater fidelity could give financial institutions a significant edge. From pricing derivatives to running Monte Carlo simulations for risk assessment, quantum computing promises to offer computational capabilities that go far beyond what is currently possible, leading to more robust and resilient financial systems, and potentially unlocking new economic models and strategies. Looking further into the future, quantum mechanics could also give rise to a quantum internet. This would involve creating a network where information is transmitted via entangled qubits, offering intrinsically secure communication that is provably unhackable due to the laws of physics. Any attempt to eavesdrop would instantly break the entanglement, alerting the communicating parties. Such a network could revolutionize secure communication, distributed quantum computing, and high-precision sensing, fundamentally changing the way we think about digital privacy and information exchange on a global scale. While the potential of quantum computing is immense, it's crucial to acknowledge that the field is still in its infancy. Building truly fault-tolerant, universal quantum computers remains a colossal challenge. Researchers are tirelessly working to increase the number of stable qubits, improve their coherence times, and develop more robust error correction techniques. The journey from the NISQ era to fully scalable quantum machines will require breakthroughs in physics, engineering, and materials science, pushing the boundaries of human ingenuity in unprecedented ways. It's a marathon, not a sprint. Governments, academic institutions, and tech giants worldwide are investing heavily in quantum computing research and development. This global effort involves interdisciplinary teams of physicists, engineers, computer scientists, and mathematicians collaborating to overcome the formidable obstacles. Major players like IBM, Google, Microsoft, Amazon, and numerous startups are vying for leadership in this transformative field, pouring billions into research, infrastructure, and talent acquisition. This collaborative push is accelerating progress, turning once theoretical concepts into tangible technological advancements. The term quantum supremacy itself has sparked considerable debate. While Google's Sycamore experiment was a landmark, some argue that quantum advantage is a more appropriate term, as it highlights a practical superiority for specific tasks rather than an absolute dominance across all computational problems. Furthermore, some classical supercomputers have since managed to perform similar tasks, albeit with much greater resources and time. This ongoing discussion underscores the evolving nature of the field and the careful definitions required as we benchmark these new machines against established powerhouses. The ultimate goal is to build a fault-tolerant, universal quantum computer capable of running any quantum algorithm. Such a machine would be able to tackle problems currently deemed unsolvable across a vast range of disciplines. This long-term vision involves scaling up qubit counts into the millions, maintaining their coherence for extended periods, and perfecting error correction to near-perfect reliability. It's a monumental undertaking that could take decades, but the potential rewards solving humanity's grandest challenges make it an endeavor worth pursuing with every available resource. Even before universal fault-tolerant quantum computers are realized, quantum simulators are already proving invaluable. These are special-purpose quantum devices designed to efficiently simulate specific quantum systems, providing insights into complex materials or chemical reactions that are intractable for classical computers. They serve as a bridge, allowing researchers to explore quantum phenomena and test quantum algorithms in a controlled environment, offering early glimpses into the power of quantum mechanics without requiring the full generality of a universal machine. This iterative approach is accelerating discovery.
As quantum computing advances, its impact will extend to education. New curricula are emerging to train the next generation of quantum engineers, physicists, and computer scientists. Understanding the principles of quantum mechanics, quantum algorithms, and quantum hardware will become increasingly important. Universities and online platforms are developing courses to demystify this complex field, preparing a workforce capable of building, programming, and applying these revolutionary machines. This educational shift is vital for fostering the innovation required to fully realize the quantum age. With great power comes great responsibility. As quantum computers become more capable, ethical considerations will come to the forefront. The ability to break current encryption raises concerns about data privacy and national security. The potential for quantum AI to make decisions with far-reaching consequences also demands careful consideration. Establishing ethical guidelines, international regulations, and responsible development frameworks will be crucial to ensure that quantum computing benefits all of humanity, rather than exacerbating existing inequalities or creating new risks. A proactive approach to these challenges is essential. To make quantum computing accessible, major tech companies are offering quantum computing as a service via the cloud. This allows researchers and developers to experiment with real quantum hardware without the enormous cost and complexity of building their own labs. Users can access quantum processors from IBM, Google, Amazon, and others, submitting their quantum circuits and receiving results remotely. This democratization of access is accelerating experimentation, fostering innovation, and building a community around quantum programming, bringing the power of quantum computing to a wider audience. Beyond computation, quantum mechanics is also revolutionizing sensing. Quantum sensors leverage superposition and entanglement to achieve unprecedented precision in measurements. These could lead to hyper-accurate navigation systems that don't rely on GPS, highly sensitive medical imaging that detects diseases earlier, or even new ways to detect dark matter. By exploiting the inherent sensitivity of quantum states to environmental changes, quantum sensors promise to unlock new frontiers in scientific discovery and technological applications, far exceeding the capabilities of classical sensing devices. It's important to remember that quantum computers won't replace classical computers. They are not simply faster versions of what we already have. Instead, they are specialized tools designed to excel at very specific types of problems, those that involve complex simulations, optimization, or the manipulation of quantum information itself. For everyday tasks like email, word processing, or browsing the internet, classical computers will remain far more efficient and practical. Quantum computers represent a powerful augmentation, not a wholesale replacement, to our computational arsenal. The journey to quantum computing began over a century ago with the birth of quantum mechanics, a revolutionary theory that upended our understanding of reality. Pioneers like Max Planck, Albert Einstein, Niels Bohr, and Erwin Schrödinger laid the groundwork for this profound shift. Their discoveries, which initially seemed counterintuitive and purely theoretical, are now the very principles enabling these futuristic machines. Quantum computing is a testament to the power of fundamental scientific inquiry, proving that abstract theoretical physics can eventually lead to world-changing technologies. Let's revisit the qubit one more time. Unlike a classical bit, whose state can be visualized as a simple point on a line, either 0 or 1, a qubit state is often represented as a point on a sphere, called the Bloch sphere. This sphere illustrates all possible superpositions, with 0 and 1 at the poles. Any point on the surface of the sphere represents a valid quantum state, a blend of 0 and 1. This geometrical representation helps conceptualize the richer information content and the ability to rotate or transform qubit states, which is what quantum gates physically achieve. Beyond error correction, scaling quantum computers presents immense engineering hurdles. Connecting and controlling a large number of qubits while maintaining their delicate quantum states is extraordinarily difficult. As the number of qubits increases, the complexity of controlling them and mitigating interactions that cause decoherence grows exponentially. Researchers are exploring modular architectures, where smaller quantum processors are interconnected,
similar to how classical supercomputers are built from many smaller CPUs.
This modularity might be key to achieving the scale required for truly powerful quantum machines.
The field of quantum algorithms is rapidly expanding beyond Shor's and Grover's.
Researchers are continuously discovering new algorithms for various applications.
From quantum simulation algorithms like variational quantum eigensolver (VQE) and quantum approximate optimization algorithm (QAOI) for chemistry and materials, to quantum linear system algorithms (HHL) for solving systems of equations, the quantum algorithm zoo is growing. This diversity of algorithms indicates the broad applicability of quantum computing and hints at the many problems yet to be discovered that could benefit from its unique computational power. While universal gate-based quantum computers are general-purpose machines, quantum annealers are designed for a specific class of problems: optimization. These devices work by preparing a system in a quantum superposition of all possible solutions and then slowly annealing it, allowing the system to settle into its lowest energy state, which corresponds to the optimal solution.
D-Wave Systems is a prominent developer of quantum annealers.
While not a universal quantum computer, these specialized machines are already being used to tackle real-world optimization challenges in logistics and finance, offering a different pathway to quantum advantage. A critical metric for qubit performance is coherence time, how long a qubit can maintain its quantum state before decohering.
Current qubits have coherence times ranging from microseconds to milliseconds, sometimes seconds for highly isolated systems.
For complex algorithms, qubits need to remain coherent for millions, if not billions, of gate operations.
Extending coherence times is a relentless pursuit, driving innovations in materials, control electronics, and cryogenics.
Longer coherence means more reliable computation and the ability to execute deeper, more complex quantum circuits. For a future quantum internet or distributed quantum computing, quantum transducers are essential. These devices convert quantum information from one physical form to another, for example, from a superconducting qubit, which operates at microwave frequencies, to a photon, which operates at optical frequencies, for long-distance transmission. Without efficient transducers, integrating different quantum technologies and building robust quantum networks remains a significant hurdle. This field is a hotbed of research, aiming to create seamless interfaces between diverse quantum systems, much like routers connect classical networks. The rapid growth of quantum computing is creating a demand for a highly specialized workforce. This isn't just about physicists, it includes quantum engineers to build the hardware, quantum algorithm developers to write the code, quantum software engineers to create the tools, and quantum industry specialists to identify and implement applications. Cultivating this talent pipeline through interdisciplinary education and training programs is critical for the long-term success of the quantum revolution, ensuring that we have the human capital to fully explore and exploit this powerful new technology. Beyond just quantum algorithms for AI, quantum principles are also inspiring new classical hardware for AI. Neuromorphic chips, which mimic the structure of the human brain, and optical computing, which uses light for calculations, are drawing inspiration from the efficiency and parallelism observed in quantum systems. While not quantum computers themselves, these developments illustrate how the pursuit of quantum computing is pushing the boundaries of computation across the board, leading to unexpected innovations in classical and hybrid computing architectures. It's a cross-pollination of ideas. One of the profound challenges in physics is understanding many-body systems, collections of interacting particles where the behavior of the whole cannot be simply deduced from the behavior of individual parts. These systems are ubiquitous in condensed matter physics, chemistry, and even cosmology. Classical computers quickly fail to simulate them due to exponential complexity. Quantum computers, by their very nature, are many-body systems. This makes them uniquely suited to simulate other many-body systems, offering an unprecedented lens into the most fundamental questions of nature and existence, unlocking new scientific discovery. The path to fully fault-tolerant quantum computers is complex and requires innovative solutions. Researchers are exploring novel qubit designs, better error correction codes, and improved control electronics. The vision is to build modular quantum processors that can be interconnected to form a larger, more powerful system, effectively distributing the computational load and enhancing overall reliability. Each increment in qubit count and fidelity brings us closer to a future where quantum computers can reliably tackle problems that are currently beyond our wildest imagination, transforming scientific and technological landscapes. What truly makes quantum computers so powerful is not just their speed, but their ability to leverage the inherent probabilistic and interconnected nature of reality itself. By mimicking the universe at its most fundamental level, they can unravel mysteries and solve problems that remain opaque to classical approaches. We stand at the precipice of a new computational era, one that promises to reshape industries, redefine scientific discovery, and push the boundaries of human knowledge in ways we are only just beginning to comprehend. The quantum future is unfolding, one qubit at a time. For decades, classical computing power advanced exponentially, famously described by Moore's law. However, as transistors shrink to atomic scales, physical limitations are becoming apparent. Quantum computing offers a pathway beyond these classical limits. It's not just about making smaller, faster circuits, but fundamentally changing the computational model. While Moore's law may slow for classical chips, the exponential scaling of quantum information unlocked by superposition and entanglement suggests a new trajectory for computational growth, opening up a realm of possibilities once thought to be science fiction. While true quantum advantage for commercially viable, large-scale problems is still some years away, the foundational research is already yielding insights. For instance, in materials science, preliminary quantum simulations are already guiding experiments, accelerating discovery even without a perfect quantum computer. The iterative process of developing quantum hardware and software is creating a positive feedback loop, where advancements in one area fuel progress in another. The impact, though nascent, is tangible and growing, hinting at a future where quantum insights become commonplace in scientific and industrial domains. For the foreseeable future, quantum computers are likely to work in conjunction with classical supercomputers in a hybrid model. Classical machines will handle most of the computational heavy lifting, while quantum processors will be used as accelerators for specific, quantum advantageous subroutines. This leverages the strengths of both paradigms. Quantum processors can solve the parts of a problem that are intractable for classical computers, and then feed the results back to the classical system for further processing. This integration is crucial for practical applications in the NISQ era and beyond. Today's most advanced quantum processors boast over 100 qubits, pushing towards the 1,000 qubit mark. Companies are racing to develop machines with higher fidelity, longer coherence times, and better connectivity between qubits. This rapid progression is a testament to the intense global competition and scientific drive. While these machines are still primarily research tools, their increasing sophistication means that the gap between theoretical potential and practical application is steadily closing, paving the way for the next generation of truly transformative quantum technology. Perhaps the most exciting aspect of quantum computing lies in the unknown unknowns. Just as early classical computers led to applications unimaginable at their inception, the internet, smartphones, AI, quantum computers are likely to spark unforeseen discoveries and create entirely new fields. The ability to model complex systems with unprecedented accuracy, to break existing computational barriers, or to simulate novel materials could unlock scientific breakthroughs that fundamentally alter our understanding of the universe and our place within it. The true power may yet be beyond our current comprehension. Embracing quantum computing requires a certain leap of faith, a willingness to grapple with concepts that defy classical intuition. But the historical pattern of scientific progress shows that humanity's greatest advancements often come from challenging established norms and venturing into the unknown. The journey into the quantum realm is perhaps the most profound of these ventures, promising not just faster calculations, but a deeper, more intimate interaction with the fundamental laws that govern our existence. It's a testament to human curiosity and ingenuity, pushing the boundaries of what is possible. The power of quantum computers stems from their ability to harness superposition, allowing qubits to exist in multiple states simultaneously, and entanglement, linking these qubits in an intrinsically connected network. This enables quantum parallelism, exponentially expanding computational possibilities far beyond classical limits. While formidable challenges remain in building robust, error-corrected quantum machines, the foundational breakthroughs and rapid advancements indicate that we are indeed entering a new computational era.
The quantum age is dawning, promising to unlock solutions to problems once thought impossible, fundamentally altering our technological landscape.
Understanding quantum power often stretches beyond human intuition, which is built on a classical, macroscopic world. But it is precisely this departure from the intuitive that gives quantum mechanics its revolutionary potential. It allows for computations that mimic the complex interplay of atoms and particles, revealing truths hidden within the very fabric of the universe. As we learn to program and control these bizarre quantum phenomena, we are not just building faster machines, we are expanding our collective consciousness, gaining a new lens through which to perceive and interact with reality itself.
It is a profound journey into the heart of complexity. The quantum revolution is not a singular event but an ongoing process of discovery, innovation, and engineering marvel.
Each step, from theoretical concepts to practical qubits, from NISQ devices to the eventual fault-tolerant machines, builds upon the last. It's a testament to sustained human endeavor, driven by the relentless pursuit of knowledge and the desire to build tools that extend our capabilities beyond anything previously imagined. The power lies not just in the machines themselves, but in the enduring human spirit that seeks to understand and harness the deepest secrets of the cosmos.